Good evening students. In this particular segment, I am going to explain you that how we can find the electric field intensity due to infinite shade in a particular space at any particular location. Okay. So, at the board, I have just considered a sheet having a negligible thickness. It having only two dimensions, one is this and one is this, and thickness I have considered negligible. Okay. And in this particular sheet, uniform charge is distributed throughout its whole surface, and the surface charge density is considered sigma, where sigma is the surface charge density and its formula is Q by A. So, for the uniform charge distribution, for per unit area everywhere charge will remain same. This is the consideration which we have considered. Now, due to this particular infinite state, I need to find the electric field intensity at a particular point. So, here we will use the Gauss theorem, and Gauss theorem is used for a closed boundaries. So, to cover this particular sheet from both the end, because the field is what? If the positive charge distribution is there, then field will be radially outward, and from the another end it will be radially inward. To cover this particular sheet, I will take, let's suppose I am going to take this Gaussian surface, and the orientation of this Gaussian surface is perpendicular with respect to this plane. Let's suppose if this is the plane, so I am just going to take this particular cylinder perpendicular to it, so that we can just close the field or close the range of this particular sheet field. Okay, so this is perpendicular with respect to the plane of this particular sheet. Okay. So here I can use cylindrical Gaussian surface or a rectangular Gaussian surface. This depends on the structure of this particular sheet or the shape and size, that which kind of the Gaussian surface you are going to use. To cover a particular, let's suppose if the rectangular sheet is there, then you have to use what? I have to use then rectangular 3D figure, so that it can cover all the rectangle. And here I have just considered a cylinder, so it's up to you and depends on the shape and size of the given sheet. Okay. So, this particular end is, let's suppose here, and this particular end, because this is perpendicular, this cylinder is perpendicular with respect to this board. So, one end will be outside and another one end will be inside, and as we know the charge will reside the outside. So, all the positive charge is on the surface and the field will be radially outward. Okay. Now, in this Gaussian surface, okay, in this Gaussian surface, let's suppose on the boundary of it, I just consider a small area dA. A small area what? dA. So, as we know that this Gaussian surface is perpendicular to the surface of this particular sheet, then its area vector will be perpendicular outward. So, now this area vector is perpendicular outward, and as we know that positive charge distribution is there, then the field pattern will be also radially outward, perpendicular outward. So, this is the direction of E also. Let us suppose the electric field strength due to this particular sheet is E, that I have considered. Okay. And if I am considering this cross section end which is perpendicular downward, okay, which is perpendicular inside with respect to this surface. So, its area vector will be perpendicular inside. So, let us suppose if I am considering dA, then its area vector will be perpendicular inward, and charge will be distributed on this particular surface as well as at the back side also. At the back side also this particular charge will be distributed there. So, field will be also in a direction of this area vector. Okay. Again I am just giving you idea that how you can think. You just think that this cylinder is perpendicular throughout this surface. So one end will be outside, it means area vector will be perpendicular outside, and one end will be inside, so its area vector will be inside. And the field is what? Field for the positive charge, the field is radially outward. So for both the end, let's suppose this hand, if the positive charge is here, then the field will be outside, and from this end also the charge is distributed, then its electric field direction will be radially outward. So like that, this seed you have to just think from both the end, from this end and from the back end also you have to just think. Okay, so same the field is outward and the same field will be inward also. Okay, let's suppose here I have just considered two portion which I have just taken an area dA, and here also dA I am just considering. One thing I can take on its curved surface area, let's suppose on its curved surface area here also I have just taken an area dA, which area vector will be perpendicular with respect to this surface. So this is the direction of area vector. Okay, but the field is what? Field is radially outward. Okay, so field is radially outward, means like that, electric field, and here the angle is what? 90 degree. So as we know, the Gauss theorem, according to Gauss theorem, the total electric flux passes through an enclosed Gaussian boundary is equals to 1 upon epsilon naught times of the total charge enclosed by that Gaussian surface. So phi is equals to, let's suppose that if the total charge enclosed by this particular surface is q, so q upon epsilon naught. This is the formula of electric flux. One more formula you know, that phi is equals to closed integration of E dot dA. Okay. Now the total flux I have to just calculate. So total flux will be due to the cross section area as well as the curved surface area. Okay. So phi I can write, phi is equals to phi cross section plus phi curve. Okay, these 2 points we have to just consider. So as it is clear, for the cross section and from the both side, the electric field will be in a direction of area vector. Okay, area vector will be also perpendicular outward, as well as the field lines are also perpendicular outward, and from this particular end, area vector and electric field will also lie in a same direction. Just imagine this board from the back end. Okay, so the positive charge will be also there from the back end also, then the field will be inside it, and the area vector, if you just consider the perpendicular cylinder, perpendicular pipe inside, so its area vector will be what? Like that. Let's suppose if I am considering this particular end, then its area vector will be like this, and the field lines also are in the same direction of area vector. So that is why here also the angle is 0, and in this particular case also the angle is what? 0 degree. But if you have considered a curved surface end, so let's suppose this cylinder orientation is like that, one surface, one of its cross section end is outside and one of its cross section end is inside. So if I am considering this cross section end, then let's suppose here I am considering, so area vector will be perpendicular outward with respect to the surface. So this is the direction of area vector, but the field is whether outward or inward. So with respect to this particular direction, electric field will makes 90 degree angle. Okay, let's suppose the field is what? The field is outward here and the area vector is vertical. So the angle will be what? 90 degree. So here I have considered this is the direction of area vector with respect to this particular surface, the perpendicular, and the field lines are radially outward, that's why it will make angle 90 degree. Okay, so total flux phi is equals to, due to cross section area, I can just write cross section. You see here, cross section and integration of E dot dA plus here also integration of E dot dA, and I can write EdA cos 0 plus close integration EdA cos 0. Okay, as we know that cos 0 is 1, so simply EdA plus EdA. Now if I am integrating dA, then we have to just put the total cross section area. So if I am integrating dA, then I will get A. It depends on the shape, that is why I am not here putting the pi r square or whatever. Here I will use total A, because the Gaussian surface, the shape of the Gaussian surface will depends on the shape of this particular sheet. So it is a generalization, it is a generalization theorem, means it is a generalization formula for the all kind of the shape. That is why I am not considering any particular shape here. Okay, so here I will get EA, and here also I will get EA, means phi cross section n is equals to 2EA. Okay, and for the curved surface end, as it is clear from the board that E and dA is making angle 90 degree, so phi curve is equals to close integration of E dot dA, which we can write, the angle is 90 degree, so what we can write? We can write E dA cos 90, and the cos 90 is 0, that is why electric flux due to curve end will be 0. So the total electric flux will be due to the cross section area end, and that is equals to 2EA. Now from the Gauss theorem we know that phi is equals to Q upon epsilon naught. So it is clear from both the formula we can write Q upon epsilon naught is equals to 2EA. Okay, and from here E is equals to Q upon 2A epsilon naught. This is our respective formula of the electric field intensity. Now Q upon A is what? It is the surface charge density, so we can put sigma, then our formula will be E is equals to sigma upon 2 epsilon naught. This is the respective formula of the electric field intensity due to sheet. Now from our observation it is very clear that here the distance term is not coming. It means the electric field intensity due to plane sheet will be constant everywhere in the space. Okay, and it will not depends on the distance. The reason behind it, because everywhere the charge is distributed in the same amount, so that it will remain constant everywhere throughout the space. Now one more thing is which is important. Let's suppose if two similar plates are there, okay, one having a positive charge distribution, another one having a negative charge distribution, having a charge densities plus sigma and minus sigma. And let's suppose due to these two states we need to find electric field intensity in between a point P. Now this is a point P where we need to find the total electric field strength due to both the sheet. Okay, so you have to understand, due to single sheet, what is the formula of electric field intensity? That is E is equals to sigma upon 2 epsilon naught. Okay, and if the positive charge distribution is there, then the field pattern will be what? Outward. Okay. So at point P, pattern will be like this, and for the negative charge the field will be what? It is inward. Okay. So what you are observing that in between the space of both the plate, the field is in the same direction. The field is in the same direction. It means that we have to simply add both the fields. So due to positive charge, the field formula is sigma upon 2 epsilon naught, and due to negative, it is also sigma upon 2 epsilon naught. And it is clear from the figure that field pattern is in the same direction. That's why the total field strength is equals to the sum of these two, the sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, means E is equals to what? 2 sigma upon 2 epsilon naught means sigma upon epsilon naught. This is the electric field intensity due to both the plates while having a same but the opposite charge distribution. Okay. So when the opposite charge distribution is there and the same magnitude distribution is there, then the field strength will be sigma upon epsilon naught. And let's suppose if same charge distribution is there, plus sigma and plus sigma distribution is there, and we need to find the electric field intensity at a point P. Then we know that for the positive charge the field is what? Outward, and here also this time positive charge distribution is there. Then from this particular plate, from this edge, the field will be like this. So inside what you are observing, the field direction in the opposite direction. It means in this particular case we have to subtract both the fields. So for the one plate sigma upon 2 epsilon naught, and from different plate also sigma upon 2 epsilon naught, but this time we have to subtract it. So in this particular case the resultant electric field intensity will be 0. So if the same charge distribution is there, then there is no field present inside the region. Okay. And let's suppose in this particular case, if I need to find the electric field intensity here or here, B. So you see here at point A, due to this particular plate the direction of field is like this, and due to this particular plate also the direction is like this. So for both the plate the field will be added. So at point A the field pattern will be E is equals to sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, means sigma upon epsilon naught minus I cap. Okay, because minus I cap is for the negative x-axis. So this is the total electric field intensity due to same charge distribution of the plate at a point A, which is left to the first plate. And let's suppose if need to find the electric field intensity at point B. So you see here at point B, if I am considering this particular plate, then field will be radially outward. Okay. And for the positive charge here also the field is radially outward. So this is the direction of the field. It means for point B also the field will be same, but the direction is outward, sorry, at the right side. So we can use I cap. So this is the electric field intensity due to sheets. So I hope that it was little bit helpful for you, for your study and for the board examination purpose. Thank you. Stay tuned to our channel.